phenol, the hint there is the ol, so that means it must contain an alcohol or what we call a hydroxy group. Okay, so phenol has this structure. It's a benzene ring with a hydroxy group attached to it. Okay, it is considered under the group of arene or aromatic compounds. Okay, phenyl with the formula C6H5OH is a crystalline solid. Now, as you know, phenyl and benzene, they are closely related. Benzene's molecular formula is C6H6. Phenyl is C6H5OH. So the hydrogen in benzene has been replaced with an OH, which is, not major. Okay. However, the physical appearance is very different. Benzene at room temperature is a liquid, okay? But phenol at room temperature is a solid. With a melting point, not so high, but it is a solid, and that is a major difference in state. So we need to address this this difference later on. Why is that phenol is a solid and benzene is a liquid? Okay, now phenol. Phenol is the starting material used to manufacture a lot of products, such as adhesive, compact discs, antiseptics. It is fitting because, I think it is during this time that some of you only realize the existence of Dettol. Okay, so yes, Dettol contains 2,4,6-trichlorophenol. Please don't make your own Dettol at home. Now we're going to look at the intermolecular forces. Obviously, there would be a strong intermolecular forces in phenol that results in the much higher melting point compared to benzene. No, you would need access to like chemicals, which I don't think you have at home. Okay, right. This is because of the presence of hydrogen bonding. If you still remember your old friend hydrogen bonding from AS, it's when you have a hydrogen attached to the three most electronegative elements, F, O, or N. In this case, you have a hydrogen attached to an oxygen. Therefore, you can have one phenol molecule can form a hydrogen bonding with another phenol molecule. Okay. Right, so the presence of hydrogen bonding is what gives phenol its distinctive physical appearance. Now, phenol contains a hydroxy group or an alcohol group and a benzene ring. Okay, so these two are, in a way, you can see it as two different functional groups. So you can see later on that when we look at the chemical reactions of a phenol, some of them will be similar to an alcohol because of the OH group. Some of them will be similar to benzene because of the benzene ring. Okay. Now, benzene ring contains carbon-carbon and carbon-hydrogen bonds. Yeah. And if you still remember carbon-carbon, carbon-hydrogen, they are treated as non-polar bonds. Okay, so it makes it non-polar. Non-polar will not form a hydrogen bond with water. It is not soluble in water. Again, this is your AS stuff. So just like an alcohol, phenol has a polar head and a non-polar benzene ring. For your alcohol, alcohols have polar head and non-polar hydrocarbon tails. Okay, right. So the presence of the non-polar benzene ring is what makes your phenol only slightly soluble in water. Okay, otherwise it would be very soluble because of the OH group. Now, moving on, we want to describe and explain the relative acidities of water, phenol, and ethanol. But first, we need to look at the structure of phenol first. Okay, so this is slightly, not easy to digest. Okay, well, not this part, later on. Right. The first thing that we want to look at before we compare the acidity of your phenol, actually phenol is a weak acid. Okay, so that's something new for you so far in this topic. Okay, Ben needs a password. Done. What's the password? How do we do that? Okay, thanks, Eric. Yep. Okay, so just to recap on the structure of benzene, since we have benzene ring contains a delocalized ring of electrons. The pi electrons in the benzene ring moves around in circle, top and below, on top and below of the benzene molecule. Okay, now, so that's this. That's the delocalized system of the benzene ring. With phenol, okay, phenol has an oxygen here. It is attached to hydrogen, but I'll just show it to you as an anion first. Okay, we call this anion a phenoxide, which you will look at later on. Now, this oxygen is sp3 hybridized. Okay, so that means you have 4 lots of that sp3 orbitals, right? One of them is being used for the carbon-oxygen bond. The other one is being used for a oxygen-hydrogen bond. And then 2 of them, sp3 orbitals, just contain the lone pair of electrons. Okay, so if I just draw this, okay, and then this is your benzene ring, right? Oxygen is in group 6, and so there are 6 electrons in the outermost shell. Oh, that's right, you don't see any drawing, thank you. I'm going to try again. This happens with your block always, and only your block. I haven't even started, you know. You know, Zoom. Let me close everything. How do I do that? Okay. Okay, let me try it again. Nope. Then I'll have to restart. I hope it's my iPad and not the Zoom, then otherwise I will have to restart Zoom again. What's the Wi-Fi name? How can you see my Wi-Fi name? Okay, let's try it again. AirPlay. Okay. Yes. Ugh. Okay, right. So as I was saying, this oxygen the hybridization of this oxygen is sp3, so that means there are 4 orbitals around it, okay? 2 of the sp3 orbitals is already being used, okay, for the bonds between C and O and O and H, right? And as I mentioned just now, oxygen is in group 6, so there are 6 electrons, 2 of them is already being used, so you're left with 4 electrons. I don't know if you can see that, but there are 4 electrons around the oxygen. And each of this pair of electrons sits in your sp3 orbital. Okay, so if you look here, that's a sp3, 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 and sp3. So 4 sp3 orbitals are all together. Okay, but that's besides the point. Now, one of the sp3 orbitals that contain the lone pair of electrons, we say it overlaps or it aligns with your delocalized ring. Okay, it is parallel to your delocalized ring. So what happens, because it aligns, overlaps, it is parallel to the delocalized ring, the delocalized system is what we say, what we call extended. Okay, instead of having this ring only in a benzene ring, it is now being extended out onto the oxygen as well. Okay, so this helps explain why phenol is more acidic than its other what we call relatives. Okay, right. I hope that's self-explanatory. This is another diagram showing you the extension of the delocalization. Okay, so you look here, this blue and yellow orbitals, they are basically showing you the system of delocalized ring top and below the plane, above and below the plane. The blue one is the one above and the yellow one is the one below, but they're all still part of the pi system. The red one is the lone pair of the oxygen, one of the lone pair of the oxygen, okay? Because this oxygen has 2 lone pairs, but it's okay, we just need one that is parallel or aligns or overlapped with the delocalized system in the ring. So what happens is that instead of having it as a circle, the delocalized system as a circle, we have it as a distorted circle like that. Okay, so that's why you see this. And that happens above and below the plane. Okay, moving on. Before I talk about acidity, I just want to remind you of an the very most common example that we use to show acid is HCl. Okay, you've learned in topic 7 or 8, I don't remember which topic number, but acid, to define acid, is a species that releases or dissociates into hydrogen ions when it is in water or when it is in solution. Okay, so dissociation is actually an equilibrium process. Okay, it is a reversible process, so I am going to first write it as a reversible, H plus plus Cl minus. Okay, so we dissociate into, it releases hydrogen ions, and then it forms an anion. Okay, so this works for anything that we classify as acid. Now, the thing with HCl is that it is a strong acid, so it goes to full dissociation. That means 100% form into ions. So your equilibrium lies onto the right side. Essentially, no equilibrium lah. Okay, so that's why we see HCl not being written as a reversible arrow, but written as a single arrow. Okay, because the position of the equilibrium is tilted so much to the right side. So we just write it as a single arrow going from left to right. Okay, so this idea of the position of the equilibrium can help us explain the acidities. Okay, right. Now, phenol is a weakly acidic substance. It's a weak acid. right? But it is still an acid, and just like any other acid, phenol will dissociate into ions, okay? But to a small extent, only very little dissociation happens. That's why we define it as weak acid, okay? So phenol, when it dissociates, you will lose the hydrogen on the hydroxy group, not the hydrogen on the benzene ring, okay? So like usual, you will release H plus and you will form an anion. In this case, in the case for phenol, the anion that we form is called a phenoxide. Okay, and phenol is a stronger acid, while I would say phenol is more acidic compared to water and alcohol. Okay, so try to avoid using the term a stronger acid. It's not wrong, it's just it can be confusing because phenol is still a weak acid. Okay, so if you want to write this down in equation, it's C6H5OH dissociated into H plus C6H5O minus. And I believe you have to write that down in your notes, okay? And in your notes, there is a list of phenol, water, and ethanol, and its pKa value. Now, pKa works just like pH, again, from topic 7 of your A2 syllabus. The lower the pH is, the stronger the acid. So if your pKa is small, it is more acidic, okay? Bigger pKa means less acidic. So don't get confused. Right, moving on. Okay, so that's exactly the same. You have to write down the dissociation equation of water. Even though we say water is neutral, yes, okay, but if you look at the dissociation of water, H2O is broken down into H plus plus OH minus. You are releasing H plus, so that is still a characteristic of an acid. It's a very, very weak acid, but still it falls under the definition of acid, okay? Ethanol, C2H5OH, dissociates into H plus plus C2H5O minus, ethoxide. Okay, and then there's your phenol. So the best way to explain the difference in acidity, okay, one, phenol being most acidic and ethanol being least acidic in this list, is easiest to compare phenol and ethanol because both of them have an OH that is off-ish like an alcohol. Okay, so that's one similarity. They're very different because phenol contains benzene ring, ethanol contains alkyl group and ethyl group. Okay, if we want to compare it with water, they're very different. So obviously, it helps explain why the acidity is quite different as well. Okay, right. So there are two ways of explaining why phenol is more acidic than any of the alcohols. So it's just not ethanol, okay? This applies to like any alcohols, methanol, propanol, butanol, and etc. Okay. One thing that you need to understand is the strength of acidity depends on the stability of the anion over the undissociated molecule. Okay, so that this means that if you have in your equilibrium you have more ions form, that means more acidic. I hope that is quite obvious, okay? More ions form means you are favoring the forward reaction, which is the dissociation or the ionization. And we know that the more ionization or dissociation you have, the more acidic your acid is. Okay, that's how we define HCl being a strong acid, because 100% of the molecule will be dissociated, fully dissociated or fully ionized. Okay, so next part comes the more, a little bit difficult part. Okay, the explanation. Again, it is not moving. Okay, right. Okay, now the first explanation involves, well, both of them will involve the phenoxide ion. Okay, so let's read the explanation first, and then I will explain. Well, I will explain as we read along. The phenoxide ion has its negative charge spread over the whole ring. Okay, now the negative charge here, usually we say that the negative charge belongs to the oxygen. Okay, because that's where the OH bond breaks. The oxygen gets the electron, the hydrogen leaves as a hydrogen ions, H plus. Okay, but because of the extended delocalization, the negative charge of the oxygen is being distributed around the whole molecule. So the intensity of this negative charge on the oxygen is less. Okay, I'm not saying that it's not negative, but I would say that the negative charge is now not concentrated on oxygen or not strong on oxygen. Okay, so in a way, the negative charge density is less or weaker. Okay, now because of that, the fact that the negative charge is not as strong, okay, it is less attracted to the hydrogen ions. So this C6H5O phenoxide does not attract the H plus. If it doesn't attract the H plus, the reverse reaction doesn't happen. Okay, and that means yes, forward reaction happens. Okay, dissociation happens, but not 100% because it's still a weak acid. Okay, before I no, okay, so that's the first explanation. Okay, this, if you read the whole thing, it will just elaborate it. It explains more, it elaborates more on the explanation. Okay, now maybe it doesn't make so much sense, but when you compare it with ethanol later, hopefully it will make more sense. Okay, so let's see. That's one. The position of your equilibrium. Is it shifting to the left or shifting to the right? But based on this explanation, we know that it will not shift to the left, so it must shift to the right. That's why you have ions. Okay. The second explanation is talking about the stability of the anion. Okay, so when phenol loses protons, okay, so phenol loses protons. Protons is your hydrogen ions, this one. Okay, the negative charge on the oxygen is being delocalized over the whole ring. This forms a more stable negative ion. Hence, ionization of phenol is more likely. This results in the position of the equilibrium to lie further. Okay, so this goes back to this statement. Okay, where if you have a more stable ion, it is more likely to be formed. Okay, so the strength of acidity depends on the stability of the anion over the undissociated molecule. So if your anions is more stable, that means ions is more likely to be formed. That means ionization happens, which means it is more acidic. Okay, so again, you know, so what? Like the negative charge is being distributed to the whole molecule. Why does that make it more stable? Okay, we will have to look at the explanation for ethanol. Ethanol, when it dissociates, it forms an ethoxide ion and a hydrogen ion. Okay, so this is called an ethoxide. Same idea, this ethoxide will have a negative charge on the oxygen, but it doesn't have a benzene ring. This negative charge is not being distributed onto the benzene ring. The negative charge is concentrated on oxygen. So you can imagine That's the first explanation, okay? You can imagine the negative charge being so concentrated on the oxygen is a strong negative charge. The strong negative charge will combine with H plus. Okay, the stronger the negative charge, the more it attracts your H plus. Here, the weaker your negative charge is on your phenoxide, because some of the negative charge is being distributed around the molecule, so the density is not as high as ethoxide. So because it is less negative, I mean, it still has a charge of -1, but the density of the negativity is less, so it doesn't attract the H plus. Okay, right. So that's the first explanation. The second explanation, not only that the negative charge is being concentrated on the oxygen, there is an additional alkyl group, and as you know, alkyl group is electron donating group. Okay, electron donating group. Oxygen is already a negative person. You have another person adding more negativity to you. You will not be stable. You will be very, very unstable. Okay, so two reasons for this. The first one, the negative charge on oxygen is strong. It attracts the hydrogen ions. Therefore, it favors the reverse reaction. Reverse is dissociation. Okay, that means less acidic. Secondly, this ethoxide is not a stable ion because it's already a negative ion and it has an alkyl group adding more negativity to it. So this ethoxide ion is unstable. It is less likely to be formed. You don't form ions. Therefore, not a lot of dissociation happens. Okay, so now if we compare it side by side, hold on, yeah. Okay, so if we compare it side by side, phenoxide is a more stable anion, more likely to be formed, more acidic. Okay, ethoxide is an unstable anion, therefore it is less likely to be formed, less ionization, less dissociation, less acidic. That's the easier explanation. Explanation number 2. Explanation number 1 is this. Since the negative charge in the ethoxide ion is not being spread out to the whole molecule, it stays concentrated on the oxygen atom. It attracts the hydrogen ions stronger. Okay, there is a stronger attraction between the hydrogen ions and the oxygen ion. Therefore, they will combine with each other to form the undissociated acid. Okay, so here you have more association, less dissociation. Now, forward reaction is dissociation or ionization, and that tells us the acidity. Reverse reaction is association. I know that my equation should be in a straight line, but there's it turns out like that when I move my PowerPoint to my iPad. Okay, so I repeat what I said. Ethoxide has a very strong negative charge on the oxygen. It has a stronger attraction to the hydrogen ions. A strong negative charge attracts a positive charge, so it favors the reverse reaction, which is association. When you have more association than dissociation, that means your acid is less acidic. Okay? Phenoxide ion. Same thing, same idea. Forward is dissociation. Dissociation, and reverse is association. Okay, remember the forward reaction is the one that determines the acidity. So this time the negative charge is not as strong on the oxygen because the negative charge is being distributed throughout the whole molecule. It still have a negative charge of -1, okay? It's just at the charge density. So now this negative charge is weaker, therefore it doesn't attract H+. Okay? If it doesn't attract H+, then the reverse reaction doesn't happen. Association doesn't happen. This means dissociation must happen. The forward reaction must happen. And when you have a lot more dissociation, your acid is more acidic. Okay? Right. So that is all for today. I want you to read back again your notes. Okay, you probably didn't have time to read because just now I didn't really read the explanation. Read the explanation again. Make sure you can digest the information. If the explanation on the notes doesn't help, you can refer to your textbook. The textbook will use slightly different term, okay, but the idea is the same. You may or may not get more confused when you read the textbook. That's up to you. But please make sure you understand this concept of acidity and the stability of the anion, because in the next topic, carboxylic acid, we are going to use this idea to explain acidity as well, okay? And you cannot run away from this question in the exam. They like to ask you this kind of question like, which one is more which one is more acidic, and explain why. Why is this more acidic than the other, okay? So it all has something to do with the anion. Okay, nothing to do with how much they release the H+. Well, it has, but the main explanation is that anion. How strong is that negative charge in attracting the H+? Okay, if it's strong negative charge, it attracts the H+. That means the reverse reaction happens. Okay, more reverse reaction happens, less acidic. Okay, if the what did I say? I think I said. Actually, I don't remember it now. That's the first one. Okay, the second one is the stability of your anion. If your anion is more stable, more likely to be formed. Okay, more ions, more dissociation, therefore more acidic. Right, Eric? I don't remember what I said. I probably said something wrong, but you get the idea. Okay. Right, so that is all for today. I am going to dismiss you. I know there is one question that we're going to do. We'll do that tomorrow. We'll see how you can understand after reading your notes. Okay, right, we have 5 minutes left. Do you have any questions?